Introduction. So now I'm going to go backwards because, just to remind you what the problem is, and you'll see that the problem that I've been looking at all week, in fact, it's the same problem as machine learning. Mathematically, machine learning is exactly the same problem. That's what's reassuring. That's why we study math, because if we study math, we know machine learning. We don't know that we know, but in fact we do, or we know the theoretical foundation, the theoretical basis. So basically, we've got direct and inverse problems. Remember, a direct problem, I give it a very, very easy form, y equals f of x, and I put a semicolon, which means, which is to say that f depends on x, which let's say it's the variables or the input, and theta will represent the parameters. Very often in parameter estimation problems or inverse problems, we use theta to represent the parameters. So you can see it's a parameter dependent system, what we call parameter dependent. And that's often the case. We see the parameters. You saw in dengue modeling and other modelings, there's always these parameters that in the equation, in the system of ODEs that we're looking for. We're not sure of them. We estimate, and we'd like to have maybe better. So the direct problem, I give you theta, and of course I give you x, and I'll ask you to compute y. I give you the parameter values, and I'll ask you to compute y. The inverse problem, I give you y, and I'll ask you to compute theta. That's difficult, much more difficult, because of various reasons. We saw ill-posedness, etc., noise, etc. So this we've seen already. Why am I losing? Oh, there we go. Oh, it's showing here. Oh, it's coming. Okay. It's just delay. Where f is an operator, an equation, a system. I don't care what f is. The theory is general. F is very, can belong to a very, very broad range of things. X is the independent variable. Theta is the parameter or the feature. In machine learning, we don't call theta the parameters. We call them the features. But mathematics for us, we call them parameters. And y is the measurement or the dependent variable. So it's exactly the context we've been seeing the last 3 days. And this is. So all you're looking, in fact, machine learning, what it does, it finds the mapping f between x, theta, and y. It's f from mapping x, theta into y. So we're looking just for that mapping f. So all the question is looking for the good mapping. So the observations are uncertain. Of course, we've seen that. C is a random variable, more generally a stochastic process. The model is uncertain. We have even unknown, unknown unknowns. There's stuff that we don't even know we don't know. Okay, but that's normal because I said the environment, the world, life, climate, disease, pandemic, propagation. There's stuff that we don't even know we don't know. That's normal because if we knew everything, of course, we wouldn't have to bother about studying. We could just stay at home and take it easy. Okay, so of course there's stuff we know. There's a lot of uncertainty in the material. When the material is the domain in which it's the air. If it's dengue, it's geographical terrain. It's inside. It could be rocks, etc. The material properties themselves, the medium through which our information is propagating that we're interested in measuring, is also uncertain. And it can be uncertain geometry, uncertain boundary conditions, uncertain inputs in signals. There's a lot of uncertainty. Whether we like it or not, there's a lot of uncertainty. So then I've shown you the Bayes theorem. I won't go back, but this, I explained to you right at the beginning that Bayes theorem solves the inverse problem because Bayes theorem gives us what we call the posterior probability density, which is the probability of theta. In other words, it gives us theta knowing y. Whereas on the right-hand side, these are things that which we're looking for theta because we're given y and we want to find theta. That's exactly the definition of conditional probability. And so conditional probability, which is the basis of Bayes' theorem, solves the inverse problem because it takes things that we know, probability of y given theta. If I give you theta, the parameters, and of course I give you x, but it supposes we're looking, I put theta here, I emphasize because that's what we're really trying to find. The first term, we call that the likelihood that we can get directly from the model. Knowing the model, we can get, and knowing theta, I can give you y. This is what we call prior information, historical data, what we know about the distribution of theta. We always know something about the parameters. We might just know that they're bounded between 5 and 8, but that's already some information that you can put into Bayes' theorem, and that's why Bayes' theorem gives us, many people believe, a much better, a much more informative solution of the inverse problem because it's using any prior knowledge that we might have had from previous experiments, from history, from documents, etc., etc. So the great advantage of Bayes' theorem, it gives us a complete solution. Not only does it solve the inverse problem, but it also gives us the uncertainty. So the solution is a probability distribution. So, it's a distribution probability. So we can say that the theta is equal to something. And we also know the confidence intervals, if you like, or the approximate. We can also measure the errors, the potential errors. We know that the value is 5 plus or minus 2 with probability 0.5, say. So you can really measure your risk. When you need to take decisions, usually decision-making or risk is taken with the risk analysis. So it depends on how much risk you're prepared to take. In certain domains, you can prepare to be more risky. In nuclear power centers, you cannot afford risk. So you have to have a very, very small, you have a very small tolerance to risk, whereas in other things, you can have a greater tolerance to risk. And then using that risk evaluation, you could, at least with knowing this posterior, this complete probability density, which is complete uncertainty quantification. So we've tamed the uncertainty, which is a bit wild because we don't really know what to do with it. But you see, mathematical tools give you a way to have a handle on this thing. Otherwise, it's you're scared of uncertainty because you really don't know what's going to happen. But yeah, we say, okay, we don't know what's going to happen, but Bayes and other people since then have done a lot of thinking about this, and in fact, it enables us to master the uncertainty. At least we can quantify it, and that's what's considered important. And so UQ would call it uncertainty quantification. The problem is the high cost. It costs a lot to do this. It's easy to write, but to compute a Bayesian solution is costly. Remember at the very beginning, so I showed you the first day, I said between 2,500 and 50,000 times more expensive to solve a Bayesian, to find the posterior probability density, solve a Bayesian inverse problem than just to solve the direct problem. That's why I say the direct problem is easy. It doesn't mean the direct problem is easy. It means direct problem, once you have the theory and you have the algorithm and you have the computer and the numerical method, the direct problem is like in a flash, you can solve that compared to the inverse problem. This inverse problem, including uncertainty quantification, is extremely expensive. But I told you, a lot of people are working on methods to enable us to do this UQ, because it's considered today that UQ is extremely, extremely important. So I told you that recently, 3 or 4 years ago, a 2,000-page book came out just on the subject of UQ, just to show that some of the best researchers in the world contributed to this 2,000-page volume. Okay, so for reasonable accuracy of the posterior, we need a good exploration, what's called the prior and the likelihood, and this implies a large number of simulations and or measurements for the evaluation of a very high dimensional interval, because a probability density is just an integral. So we have to explore an integral in a very high dimensional space, and this is complicated mathematically, not just mathematically, but practically it's complicated. Okay. So, okay, I won't go back to this. We saw this. This is a recap. It's good to see what we've done until now. We use the model to generate the measurements. We call them y hat because they're approximations. Why? Because we don't know the true value of theta. If we knew the true value of the parameters, we wouldn't be here, right? If we knew exactly what parameters put into the model, well, okay, we would be. Some of us would be here, but I wouldn't be here explaining to you why we need to do more. And then we defined our cost function, some kind of function this is the error. Sometimes it's called the error function. Sometimes it's called the loss function. In machine learning, it's called a loss function. In mathematics, in optimization, we're accustomed to calling it a cost function in some norm. And the whole idea is to find theta star, which is the argument of f of theta that gives the minimum value. That's what's called the argument problem. So that's a classical optimization problem. And we have a constraint, which is a PDE. So it's what's called constraint optimization. And constraint optimization is something that the mathematicians know very well, and we can solve this. Okay, the problem, again, some difficulties, okay? Life is not as easy as we would like it to be. This inverse problem, this theta star equals argument, looking for the minimum, optimizing or minimizing this cost function, is very ill-posed, has local minima. In other words, it's not a nice parabola, right? It's not a nice convex problem. It's a messy, what I call a messy optimization problem. It requires computation of a gradient, needs regularization. And it has problems with noise and uncertainty. Of course, if you have something noisy and you're trying to look for gradients, of course, the gradients are going to go crazy. Once they'll be positive, once they'll be negative. They can change a lot or not change at all. And if the cost function is very mountainous, up and down, you've got changes of sign of your gradient, and you never really know whether you're at what we call the global minimum, the best minimum, or you're at some local minimum, some intermediate valley, which is not the steepest valley where you would like your function to be to get the minimum value, which means you get the minimum error, which means y hat is as close as possible to y. Y are the observations, y hat is your forecast of your guess or your model solution. And if you have a good y hat, it means you found the good theta hat, which means you found the good parameters. So you've solved your inverse problem. You found the parameters that you need so that your system of ODEs or PDEs gives you a better modeling or a better evaluation of the reality. Reality being given to you by the y, which are the observations. So you're really taking into account any observations that you might have, okay? So that's classical inversion. Has it moved? One more. No, hasn't moved. Yeah, people are losing something. Okay, here we go. So, but as I say, don't worry, solutions exist for this. The problems are difficult. So we've heard about MCMC, Markov chain Monte Carlo. Bayesian optimization is something very interesting, but we don't have time to go into it. It's another technique that uses Bayes' theorem to sample. We're looking at this problem. Remember, we were looking for this probability distribution function, P of theta given y. There are methods, very, very sophisticated, very good methods. Whereas classically, we've seen that there's also adjoint state methods, and then we can use quasi-Newton minimization techniques, regularization techniques. So there are solutions, okay? But even with these, the inverse problem is hard. Huh? I don't want to hide the truth and say, well, look, inverse problems are easy because look, I showed you some things that work. But inverse problems, real inverse problems, are hard. It's a challenge. These are nice. These are really challenging problems. Very, very challenging. So why do I say all that? Because up comes what's called the new kid on the block. The guy arrives, but full of energy. It's machine learning. So machine learning has maybe some things to propose. So there are two major properties of machine learning that potentially can be very useful for us. When I say for us, it means to solve our inverse problems, environmental problems, medical, whatever you want. The two properties that are not often flouted, but because machine learning people take these things for granted, but because they don't really think about them. But in fact, fortunately, these things exist and they have mathematical implications, consequences that are very important for us. And the two properties, which I'll point out to you, just so that you know that I'm showing you what I consider the trustworthy or the explainable part of machine learning. This is what interests me. The unexplainable part, I'm scared of it because for me, it's like black magic. Huh? I really don't know how they do it. I don't know why it works. Neither do the computer scientists, but they're not. Mathematicians are much more, we're anxious, we're worried. We're worried that, we give a solution, but is it a good solution? Is it unique? Is it stable? Is it bounded? Has it got finite energy? We ask ourselves too many questions, but we have a good reason because we know that otherwise, what we call skating on thin ice. You don't have much ice here, but in the northern hemisphere in Europe, there's ice, and if you skate and the ice is very thin, you might fall into the cold water, and that would be great. So it has two fantastic properties, really amazing properties, which are universal approximation and what we call autograd or autodiff, which is automatic differentiation, or autograd, which built in. Now, these are things that I'll explain to you that the interest that was. Classically, or using calculus, or even using Bayes, classically, you saw we want to minimize a loss function, an error function, an object, a cost function, and we would like to get our hands on the gradient because we have the gradient of J. We call our cost function J, or sometimes in machine learning it's called L, the cost function, because it's L for loss. It's a loss. It's either an L1 loss or an L2 loss, or an L1, L2 loss. They use quite sophisticated loss functions. There are many, many possibilities. And always said that if we have the gradient and we want to minimize, then at least having the gradient ensures that you'll arrive at a local minimum. Maybe not a global, but at least a local minimum, and you'll arrive very, very rapidly if you have the gradient. So finding gradients is one of the, or obtaining gradients is one of our major problems. And you saw the gradient of this cost function J or loss function depends on theta, and theta depends on a partial differential equation or a system of ODEs. So you see, finding the gradient is not like taking f and f primed and putting f primed equal to 0, right? Taking the f dx. When we have a function of a scalar variable, life is easy. Huh? That we all did in calculus when we were much younger, right? And we had no problem. So we said, what's the big deal? The big deal is this, as I told you, that we're differentiating with respect to a function. Theta is a function. It's a function of space and can be a function of time. So we're differentiating J with respect to theta. Why? Because we want to find the value of theta, which gives the minimum of J. Huh? Okay. After the minimum value, we're not really interested. We're just interested in that theta, the theta star, which is the argument that gives the minimum of the cost function. And so if we have some kind of automatic, and in fact, one of the greatest achievements for me of the machine learning, deep learning community is that they found a way to do automatic differentiation. Automatic, you say, wow, that's great. And it can differentiate it with respect to X, yeah, sure. But it can differentiate with respect to functions. It can do functional differentiation extremely rapidly and extremely rigorously. This is incredible. We get, this is why there's a lot of potential. That's why many people today in inverse problem and DA research are looking very closely at machine learning because of this property. And I'll explain a little bit. I don't have time to go into it. It requires a whole course, not a whole course, but a lot of, let's see. Okay, so here we go. So I wanted to show you something about machine learning. So we don't have time to do machine learning. I'll come back another time and we'll do machine learning. But machine learning, basically, this is what's called a fully connected neural network. So this is one of the simplest neural networks that is one component in deep learning, what we call deep learning algorithms. They're all based at some point on this kind of architecture, but don't very worry. Basically, we have an input layer and an output layer, and between the input layer, we have what are called hidden layers, but I'll show you the mathematical. There is a very nice, very simple, relatively simple mathematical formulation of this neural network. So the neural networks are based on rather reasonably simple mathematical formulation. I want to show you that because then I can explain to you what this universal approximation theory. I didn't say to you what the universal approximation was. The first property. The universal approximation says that machine learning based on this very simple architecture, which is usually it's the fundamental building block. This fully connected neural network is the building block of much more sophisticated neural networks that we speak about, that are used by Google and others to solve very complicated computer vision and speech recognition problems. But they all come, at some point, they use this type of building block. And then deep learning means there's many, many, many different types of architectures all put together in a big, I call it a big mess, but so. And the amazing thing is that this basic building block possesses what's called the universal approximation property. I'll show you the universal approximation property, which means, in fact, we can approximate any reasonably smooth function, and even reasonably smooth function to a required degree of accuracy. It's really a universal approximator, which means it can fit any function, even if you don't know it, with precision. So how does it work? Well, I'm not going to go into this. This is how it works, but basically one has what are called weights, the W, and every weight has coefficients, and we have here you see this is just a polynomial, a linear polynomial, W1 times A0, W0 times A0, W1 times A1, and the other index means that we're in the first layer, because I said they're layers. So in fact, we end up with an inner product, W dot A, if you like, and then you see there's the sigma. Sigma is a nonlinear function that's called the activation function, and it gives some nonlinearity, else we would just have a linear model. And then what we do is, from layer to layer, we do a composition of functions. So you see my y, if I had a single layer, would just be wx plus b. So you can see there's what we call a kernel inside the sigma, and we apply the activation function. And these activation functions give the nonlinearity. And this is what makes it look like neural networks. This is the analogy with how the brain works, is that the brain also, you have an input signal, X, you have something going on, and then you have an activation which says the neuron is going to fire or it's not going to fire, and it gives an output, which is the signal that's sent to, it sends to my arm to go like that, right? So this is my neural network is actually doing something much more complicated, but basically it can be resumed by this. So this is for a single hidden layer, and then what we do is we add layers. So to add layers, in fact, we make a composition of functions, functional composition, and we get the following two theorems, which are really amazing theorems that said, if sigma is any continuous sigmoidal function, this is the first one of the earlier results by Asch and Sibenko, then we can show that this composition of functions, or a sum of alpha times the sigmas, they are dense in the space of continuous functions, which means if it's dense in the space of continuous functions, it means that this g of x can approximate to arbitrary accuracy any function in the space C. So you don't really have to know the function. What's this function f? We saw f or g. It's the mapping between my inputs and my outputs. And it takes, you don't have to know the equation. If you can find the mapping between input and output, then basically you've solved the problem without even knowing the equation of the model, right? And the noise, whatever. And then a supplementary theorem, which was 10 years later by Pincus and some other people, there's also some Chinese who did this, said that the space of single layer neural nets, which is the span of, I showed you these activation functions acting on a linear combination. This is just a linear function. W are constants, x is x plus b. This is just ax plus b. We know this very well. Is also, this is dense in CM1 to MS, where S is the number of hidden layers. So we have what's called a second approximation theorem, where supposing that sigma is not polynomial, then the single layer, just a single layer of a neural network, is already, in some sense, a universal approximator of continuous function. And then what's maybe one of the most interesting of all theorems is the theorem of Chen in 1995. These guys were electrical engineers, in fact. This came out in a journal of IEEE. It didn't come out in a math journal. These were people who were interested in doing signal analysis or image analysis, and they found this theorem, which is very good, which says that if sigma is continuous and non-polynomial, and they put it in the good Banach spaces, K1 and K2, and there's a compact V in the space of continuous functions, and G is a continuous operator from V into C, then for any epsilon, it's a classical approximate. Now we start to feel comfortable. The mathematicians feel comfortable when they see this. So we say, everything's okay, we can sleep, we can use these results. Then for any epsilon, there exists positive integers M and P, and constants C, Xi, theta, and W. Mostly it's the W's that interest me and the X's, such that G of U of Y, this gives me the function approximation. So I can have a function U as a function of Y minus, and this part on the right here, the double sigma, that's my neural network with multiple layers. So I can have multiple layers with my neural network. You recognize a single neural network is here, and we multiply it by another. This is the composition of functions. So it will be the difference between any operator G, it's just a continuous operator from V into C, and my neural network approximation, which is all this guy here with the many layers, is as small as we want. So you give me an epsilon, and I can find you the sigma, the Xi, the theta, and the W, such that this approximation is valid. So this is a very, very important theorem. And in fact, I'll show you an algorithm afterwards, or a method that takes this theorem and copy pastes it into an algorithm. And so we can take, for G of U of Y, we can take exactly, if we can copy this formula, you saw for Kalman filters, all I did was I copied the formulas, right? I did the calculus or the statistical analysis, and I just copy the formulas. That's why the theorems are powerful. If these theorems give you a result like this, it's enough to copy the formula, the equation, and I know that I can get as close approximation as I want to any g of u of y. Okay, I've called it u, sometimes I call it x. Here it's u just so it can be more general. It's used, we're used to using u because u is usually the solution of wave equations, reaction diffusion equations, etc. Okay, so that's the first point, universal approximation. Now let me tell you quickly something about automatic differentiation, then I'll show how we use these things to solve the inverse problems and to solve PDEs, first of all, and from PDEs you'll see solving an inverse problem. In terms of machine learning, it's a triviality. If you can solve a PDE, in other words, you find the mapping between the input and the output without knowing the model, then solving the inverse problem in terms of machine learning is completely trivial. It just means to add a supplementary, another term to the loss function. You'll see that this is what makes it incredible. It's like magic, but in fact, we've seen that there are theorems behind that. Now, doesn't mean that it's easy and doesn't mean that you don't need a big computer or a lot of time, but theoretically, at least, it's completely solid. It's okay. So the whole idea of what we call training or learning. So, you know, machine learning has the word learning in it. What's the learning? The learning is finding the coefficients W that minimize the training loss. Now, the loss, we define a loss function, which means the difference between the prediction that comes out of the neural network and our observations. We always have our observations with which we compare. Okay, in image classification, you've seen, or you haven't seen, or in speech recognition, we know we have observations. We have the speech, we have the images, we know what the speech means, and we know what the images are. We know this is a dog, this is a cat, this is a horse, but the algorithm doesn't. The algorithm has to learn, right? So it doesn't know initially what these things are. It has to give it. So we can always calculate this training loss. The difference between what is done, classically, we always use normal gradient methods, so steepest gradient, quasi-Newton, eventually Newton methods. But in machine learning, what the people who developed machine learning, this is basically work of the last 10 years, developed what's called the stochastic gradient method, which is extremely, extremely powerful because it minimizes noisy loss functions. If the loss function has a lot of noise in it, and we know that images, you know, the cat can be behind, in a shadow, the cat can be turning to one side, the dog can be next to a tree, and you understand that this creates a lot of noise. The images are not clear. It's not clearly a dog, clearly a cat, okay? So the machine learning algorithms that were developed originally had to deal with a lot of noise. So the loss functions are very noisy. A small change can create a big change. A small change in the image creates a big change in the loss function, among other things. And they're very irregular. And it turns out that stochastic gradient methods, which is an intelligent way of taking, instead of, the idea of a stochastic gradient is that if we have a minimization problem, you saw our loss function, we have to minimize J with respect to theta, but instead of minimizing over all the possible values of theta, what we do is we take random subsets and we minimize over small random subsets. And we can show there are very nice mathematical results in the last 5 or 10 years that shows that the stochastic gradient, by sampling randomly inside the space of our parameters, or what the variable that we seek, the theta, in that theta space, we can prove that we obtain, we tend to a minimum. We tend to a minimum. And why is it important here? Because you saw that we're replacing our theta here in machine learning by all the weights W. And the problem with machine learning is that W, the dimension of W, becomes extremely large. It goes to tens and hundreds and thousands of millions, right? So the big neural networks that are doing Google Translate behind, or doing image recognition, they are using billions. They're using a vector W that is of dimension of 10 to the 9, 10 to the 10, huge, huge. And obviously, if you want to minimize over such a large space and you take the whole space, it creates a minimization problem which is actually untractable. You cannot do it. So the stochastic gradient is a very, very, very clever way of taking very small subsets of this vector W. We don't take the first component and the second, but we take randomly, and it can be shown that by taking random small samples, sometimes the samples are only of dimension 1. So we can solve a sequence of one-dimensional minimization problems, and as long as we sample these variables, these single scalar variables of the big vector. Stochastically, randomly, we have a convergence theorem. Okay, you might have to do a large number of stochastic gradient samples, but each sample, a one-dimensional inverse minimization problem is solved extremely quickly by the computer. And in addition, as I said, we have this automatic differentiation, auto-diff, auto-grad, which makes it even quicker. So as I said, the gradient is computed by AD. We call AD automatic differentiation, sometimes called autograd or autodiff, where the output is differentiated with respect to the weights based on the chain rule. We just use the chain rule of differentiation of a composite function, and AD implements this in automatically without us having to do the differentiation ourselves. So it can differentiate the cost function J or L with respect to the WI, which for us it comes to some extent gives us the theta. And we can show that what's used in machine learning algorithms is what's called reverse mode at automatic differentiation. Why the reverse mode? Because we start from J and we go back to W. dJ, dW, we have to know J first. So to know J, we have to go forward, right? Forward, because J is the cost function or the loss function. J requires the output of the neural network. We compare the output to the observations. So dJ d theta means we have to go one run forward. We have to go through a neural network in a forward direction. It's like solving the direct problem. And then to compute dJ dW, or the gradient of J with respect to W, we call it going backwards. We go backwards through the chain that led us from the initial data or input data to the output. And by differentiating backwards using Leibniz's rule, using composite or the chain rule, one has something which is exactly equivalent mathematically to the adjoint state method. That's why the adjoint state method, I insisted. You know, if we want to understand machine learning and we want to be able to use machine learning intelligently, then we need to understand the theory. Yeah? And the theory here is reassuring that these supposedly magic methods used by machine learning algorithms are in fact just universal approximation plus adjoint state method, which has been algorithmically programmed in a very, very efficient way, because machine learning, okay, you want to do things quickly. You don't want to wait hours for your Google Translate to translate, right? You don't want to wait hours for your Tesla, for your new autonomous car to recognize the fact there's a pedestrian or there's a stoplight and it has to stop. Huh? So these things have to be done fast, extremely fast. Okay, even though there's a difference between training and inference, but I won't go into that. But somehow even the training has to be done extremely quickly. So that's why. So there are a number of approaches. I won't go into for solving. Let me show you. So you see what I've shown you here is what's called a data-driven approach. Huh? I'm not using a model at all. There's no model. There's no PDE. There's no ED. I told you, in data we trust. You know, can you throw away the models and just use the data? Saying, because why? The data says. The data says, or the people who believe in data say, well, the data knows the model already, so why bother looking for a model? We spend all our lives looking for models, and the people, the machine learning people, they say, but you guys are crazy. You've got the data, and the data knows the model. You just have to pull out the knowledge of the model, the information of the model from the data, because the data, if anything knows the model, it's the data, because it went through the model. And it means you don't really have to know it, because you've got the data. You have, when I say data, it means you have measurements, right? Observations, right? Okay, so okay, but, all right. That in theory, they're right, but in practice, of course, it doesn't work so easily, and somehow it is, but it does, I'll show you this. So, there are various data-driven approaches that we can use, and what I like to do is the last two or the last three, or some combination, is use intelligently, not a purely data-driven approach, but to use a combination of data and model-driven. Okay, data and what I call physics-driven, or sometimes they call them physics-constrained machine learning. That's the whole idea, is physics-constrained. You want to constrain your machine learning, because the machine learning algorithm, it doesn't know the physics. It doesn't really care. It's looking for the coefficients W, and okay, we have the activation function sigma. At sigma, usually we we give one activation function. We don't usually search for activation functions. All we search for are these coefficient W, which are coefficients of a linear combination of the inputs X. You remember it's WX plus B. Okay, there's what's called a bias or an offset. And then we have just WI times XI. The XI are inputs. The inputs we know. These are the guys that come in on the left, on the left of our problem, and they go across to the right. I always go from the inputs to the outputs, left to right. Okay, that's the direct problem. So the machine learning, it says, I don't care, I'm just going to look for W's. So this is a completely data-driven approach. The problem is when it finds what's the closest, the best W's, how does it find it? Minimizing the cost function, minimizes the cost function with an adjoint method, which we call autodiff, and the stochastic gradient, because it's a very, very large, okay, it says, okay, it's true that I won't be able to solve the inverse problem unless I make a very, very high dimensional approximation, and neural networks make very, very high dimensional approximations. I told you the dimension of W can be 10 to the 6, 10 to the 7, 10 to the 8, 10 to the 9. You'll see that even if we do small neural networks with 100 or 200 or 400 or 500 or 1,000 unknowns, already the computational times start to become quite expensive. In other words, it generates, even though theoretically it works, it generates a difficult optimization problem, but theoretically it's a good problem which has a solution. So I'll show you also very rapidly what we call physically constrained neural networks. Then there's another way of looking, which is called operator learning, which is a combination of data-driven methods with system identification. I'll show you very rapidly what it is. And then one can just say, okay, well, I don't want to use the neural network itself, but maybe I just want to use the autodiff or the autograd. The autograd, which is this capacity, the capability of machine learning algorithms or machine learning libraries, which still are libraries available, because they do very efficient gradient computation. And then I can use my favorite quasi-Newton method or something else to do the minimization. But at least the gradient I get more or less for free. I'll explain more. And then one can do combinations. So this slide, for me, it's the research of the next 10 to 15 years. There's so much stuff to be done inside here, which is just starting to be done. It's the research in this direction of how to harness the power of machine learning algorithms to solve direct and inverse problems based on PDEs. It started maybe 3, 4, 5 years ago, not much before. All the papers, the earliest papers are 2019, 2020, 21, 21, the last 3, 4 years. Everything has started to move, and there's a big effort, especially in the US and to some extent in China, to start investigating this, because you'll see there's a lot of potential. Okay. So, more and more software is becoming available. Okay, there's even semi-commercial, already we've reached the stage, anybody who's interested to see, I recommend you Google DeepXDE. DeepXDE is an attempt to make a kind of MATLAB package for, for solving differential equations using deep learning. Okay, so this is written by people from Brown University and University of Pennsylvania. George Karniadakis, and it's the first attempt to to make it general public. In other words, any graduate student can take their package. There's a Git, there's examples. It's very, very well documented. There's a very nice paper, a review paper in CIMPA Review, which is a journal that publishes reviews which give a relatively simple introduction to this thing. There's a very nice paper on DeepXDE. And there's the GitHub, which contains all the code, and this is something, it's an easy introduction, so you get a feeling of how can a neural network solve a PDE without any knowledge of the PDE? Okay, we will need some data, okay, so usually we use the PDE to generate the data, but then we pretend, we suppose we don't know the PDE, and we just have the data, which is the solution, which are solutions for different combinations of input data or different perturbations of the input data. Solutions at different points in the domain, and then we can. So they're becoming semi-commercial. Even NVIDIA has released a library to solve NVIDIA, which it's like computer games, right? What are they interested in? game, you know, they're just selling lots of games to kids, you know, to get them addicted to the internet. But NVIDIA is interested in solving PDEs with deep learning. That means when NVIDIA and these guys, when the big, you know, the big 4, 5, 6, whatever, when the big GAFAM get interested in something, you know that there's some interest. Okay, so this is just starting. This modulus came out maybe 1 year ago, and then there are quite a few academic software packages available. I don't, you know, so I give a list here, and you Google any of these things, and you'll find many. And so I have some links here. If you take my PDF, usually you can click directly on the links. I think most of them made them clickable, so you can just click and it'll take you directly to the web pages where you can find something more data, more information about it. So let me speak rapidly what's called surrogate models. So the whole idea of a surrogate model, sounds like we can call it a reduced order model, is that we want to replace a complex system with something simpler. In other words, basically we want something that can do the input to output map without the expense of solving the whole PDE. Huh? And surrogate model, it's a whole domain. It's just been used for a long time. It's not new. But the new thing is that the machine learning mapping, in other words, you can sort of the network, that's the final neural network that's been found, can be used as a surrogate model, because once you know the machine learning mapping, in fact, what do you know? You know the W's. The W's are just, what are W's? They're just coefficients of a linear combination of functions. Huh? If you ask a computer to evaluate a linear function, the computer says, you know, that's an easy problem. Computer evaluates linear functions, and even composition of linear functions with activation functions. That's an immediate, it takes milliseconds, milliseconds to solve an extremely complex problem once you know the mapping, once you found the F. But we saw we have a universal approximation theorem, so if you work hard enough, if you have a good enough neural network, you guarantee to have the good F, the good mapping between the X and the Y, between the inputs and the Y, in other words. So if you have a surrogate model, then you can do what we call inference. You do the learning phase. It's long, it's laborious, it takes a lot of patience, tuning what we call hyperparameters, feature selection. There's a lot of stuff that goes with it. Okay. It's not as easy as it looks, but it can be done. Finding the good WIs, which are just, and once you have these WIs, you just have to evaluate a linear function for a computer. That's completely trivial operation. It's just multiplications and additions. Even there's a million, your computer can do a million additions extremely quickly. It doesn't take much time on a computer. Usually you don't go as far as a million. And these are surrogate models. So surrogate models, there are many other definitions of surrogate models. So if you want to, in my digital twin book, I have a whole chapter on surrogate models and reduced order modeling, and it goes back to reduced order modeling, and this is classically well-known stuff that's been developed for many reasons over many years. So, okay, so surrogate models, they're also known as response surfaces. In some domains, it's called a response surface. Sometimes we call them black box models. Sometimes we call them meta models, emulators. It depends. They're simplified approximations of a more complex, higher order model. And these models are used to map input data to output data when the actual relationship between the two is either unknown or computationally too expensive to evaluate. So, you know, we might have a very complicated system of equations, nonlinear or a large number of equations, but it might be partially known, or too expensive. And in that case, if we can find a meta model or a surrogate model, or an emulator or a black box or a response surface, these are all synonyms. We can replace, to some extent, these expensive, complicated simulations by a simpler model. This is a very important point. It's a subject of active research also. Okay? For example, one can use classical ML, machine learning and regression techniques, to create these surrogate models. And that's the idea of ML. That's why they came to us and said, yeah, we've got something to sell you, you people who are doing differential equations. We can replace your very complicated system by a polynomial. In fact, it's just a polynomial, or it's a nonlinear polynomial. And once you have a polynomial, for us, for a computer, for a laptop, for evaluation of a polynomial is a completely, as I say, completely trivial operation for a computer. And if I replace your very complicated, turbulent, atmospheric conditions, topography, vegetation, climate, dengue, all together. I just say, okay, that's the model, but I've got data, and the data knows the model, so let's just work with the data. I can get a surrogate model, which is nothing else but a linear combination multiplied, a composition of linear combinations multiplied by activation functions, which once I have that mapping, I solve my problem in seconds, literally in seconds, sometimes even in milliseconds. Okay, so this is amazing. Instead of spending 100 or 1,000 or 1 week solving a problem, you can literally solve the problem in seconds. And you get speed ups of the order of 10 to the 3, 10 to the 4, 10 to the 5, 10 to the 6, compared to solving the complete model, if you have a good surrogate model. So this is not just saying, okay, I get a speed up of 2x, I get a speed up of 10 to the 4, 10 to the 5, 10 to the 6, when it works. Okay. Not so easy to make it work, I admit, but the potential is enormous. You see, this is why I find it, as the Americans say, very exciting. It is very exciting, really, with all, and I'm very critical of these things, but there are a lot of things can be used. So they're even simple ones. So basically, what the idea, and this you must keep in mind, this, I like this flowchart, my sumo flowchart. Sumo, it's like the sumo wrestlers, you know, in Japan. But sumo means surrogate model, but it's very, very strong, because basically, I have my design parameters, this is one way of, and I have my output, okay? And I want to map from the design parameters to the output. So these design parameters can be material properties, they can be boundary conditions, they can be initial conditions, they can be the shape, geometry for shape optimization, whatever you want. They can be the source function. I don't know the source function, or I don't know the location of the source function. You can put anything you like in the design parameters. These, you just parameterize them by a vector theta. You can perform simulations if you like, and with the simulations, you can create a surrogate model using the simulations. And once you have the surrogate model, you can do the inference. So you see what I showed you, the red arrows are the expensive parts. So the expensive part is the simulation, going from design through my model to the output and doing the training. But once you've done that, then you can take the blue path. You go from design parameters through the surrogate model. You see I put approximately equal, because it's an approximation. But I have a good approximation of f without, I call it f hat. Always an approximation is always a hat. And if I go along the blue path, speed up of 10 to the 4, 10 to the 5, 10 to the 6. I'm not exaggerating. So a computation that would take 10,000 hours is finished in 1 hour. Imagine 10,000 hours, you know how many days that is? Okay, that's months and months of computation you do in 1 hour. Okay, that's not bad, all right? So you see why I say we'd better have a look at this, because if we want to solve complex things with stuff we know and we don't know, and it's badly known, but we have data, and we can do this training part, the red part, then it's worthwhile. What we stand to gain will far outweigh what we did, the time that we're going to spend in the training phase. Because once you finish training, you have a surrogate model, sumo. You've got these heavy guys you can push. They can knock down any problem. You give me a big problem, these sumo guys are even bigger. They're going to knock it down. Okay, so that's the idea. But okay, it's not. In theory, this is very, very nice. It's beautiful, but of course, there's some work. The work goes into the work is the red path. That's what we're here to do, is to do this red path, but knowing that you only have to do it once. Okay, once you have it, okay, then tomorrow you might have a new problem, but once you have experience of doing the red path with another problem, you might have new data. Sometimes you can just add the data and do partial retraining, but you can always retrain a network. A network is not trained once and that's it. You can always retrain. You can start from the network that you found here, the surrogate model you found here, and use it as an initial condition, because what's initial conditions? The initial values of the WI. Okay, we mathematicians say, well, what's the network? Oh, it's a vector of coefficients, WI, that we seek as to find the argument, the minimal value, to minimize the loss function being the difference between what the neural net gives as output and what our true observations are. So that doesn't mean that you have to retrain from zero. You can start from the last surrogate model you had. How do you start? You just use the values of WI from the last surrogate model. You use them as initial values, and you let your machine learning algorithm, when you get new output, just say, you know, something has changed. The epidemic has moved to another phase, and you want to be able to predict more closely this other phase. this chart you find on my website, on the website of on my GitHub website. I've given you references, markasch.github.io/something DTTBXV1. You'll find this, and I have a blog, what's called a blog, because my book became so long that I had to stop because I was never finished. I was getting close to 1,000 pages. I said, that's enough, but I said, I have to continue writing. So I decided to continue writing on the website. So the website contains this stuff because I started thinking about the subsequent, after I finished the book, there wasn't enough space. The book was getting, you can hardly carry it. It becomes too heavy to carry. Okay, so just to show this stuff, all that you see here, you can find on my website. Okay, you can even download the images. So, okay, that's a lot of motivation, and then the rest is detail. This motivation is, remember the motivation, because then afterwards, now it's for you guys to play, to work. I consider mathematics as playing, but it's work also, of course. So I said there are a number of techniques, and then in the rest of the talk, I'll go very rapidly over the techniques. I won't go into much detail. But just to show that for what we call physics-constrained machine learning, there are two approaches. Either you can learn the solution, or you can learn the operator. There's two ways of doing this, and using the two theorems that we saw before. And we really don't have time, but the idea is to replace all our traditional methods. Sorry, Marilia is teaching you finite differences, finite methods. I say, garbage, delete. No, that's not true. You can replace all the traditional numerical discretization methods, ODE solvers, Runge kata, garbage, out. We're going to use data now, but it doesn't work now. It doesn't work using exclusive data because, as I said, the neural network doesn't know the physics. So the neural network might give you a solution, but there's no guarantee that that solution is a physical solution. It might give you a non-physical solution. That's very, very dangerous. If you cannot check that the solution given to you by the neural network is indeed a physical solution, it's just a mapping. The neural network is agnostic. It doesn't care what kind of PDE, ODE, linear, whatever you want, if finite difference, finite element, finite volume, it doesn't care. Really doesn't care. It just looks for that mapping, these WIs, okay, and the sigmas. And so, even though one could replace them, one has to be very careful because there's a high probability that you generate a solution, that the neural network gives you a solution that is not necessarily a good solution in terms, good meaning means it doesn't respect the physics, and you have to be able to check it. So the neural network, I told you, just learns an approximate solution. In fact, it learns an approximate solution or an approximate or a mapping. And then how? We just constrain the neural network to minimize what's known as an augmented loss. If you want, now we want to do physics constraints. So all we have to do is we have to add to the loss function a constraint which includes the PDE. So in fact, we're going to just put the PDE into the loss function, because I told you, the neural network, it looks for WIs. It doesn't have any equations. So if you want to be sure that the argument, the minimum that you found of this, I call the theta or the vector W, respects the physics, well, you can just put the physics into the cost functions. You have L1, which is the loss function for the neural network, okay, for the WIs, and you can have an L2, second term, and L equals L1 plus L2, and the L2, the second term, is just a loss function which compares the solution to the solution of the PDE. So you can put the PDE as a constraint into your loss function. Under the PDE, we say, but the PDE contains derivatives. How do I do derivatives? Autograd. Derivatives for neural networks are easy because neural networks use autograd, use automatic differentiation to find the WI. So I'll say, okay, that's great. I'm going to take that automatic differentiation. I'm going to use it to calculate du dt minus Laplacian of u. I can do all those. They're just partial differentiation, partial derivatives. I can use the autograd to calculate those partial derivatives. So I can add an extra term to the loss function and have what's called a composite loss function of two terms, which includes the PDE. This is all in theory, but it's rigorous theory. Afterwards, in practice, there's a lot of adjustment of parameters, etc., etc. Okay, and then I add these little functions, and then so weights and biases. Weights are the WI, biases are the BI. Is the constant term. So this is why you can see that there's something here. All right, I'm transforming a difficult problem into something. So anyway, just suppose that this is I just show you an example. Huh? So if F is the PDE and B are the boundary conditions, then what we call the pin loss, we take a sum of two loss functions. And if I have an inverse problem, I can even add a supplementary term, a third term with a different weight. These are not the same W's as before, sorry, I use that again. And you see the same, you can add a term which includes also the loss function that I was using right at the beginning, yesterday and the days before, for solving my inverse problems. You can even add the inverse problem loss function to the loss function. The neural network doesn't care, huh? It's just minimizing a loss function. What I can choose what I put into that loss function. I can just make L1, L2, but I can do L1, L2, and I can add the PDE, and I can add the loss function of the OD, of the PD, of the inverse problem. So you see, this is amazing, huh? Okay, it really, I mean, theoretically, it stands up. Okay, so here lambda the inversion coefficient. So in fact, I can find the lambdas, which just say I call them lambda now. Sometimes I'm changing notation now, which are the coefficients that I'm using in my inverse problem. So and then I get a more complicated argument, a more complicated minimization problem. It's called, we call it an augmented optimization problem. We augment the optimization vector and the parameter vector or the unknown vector by supplementary. We have a theta vector and a lambda vector. The theta vector was for the WIs, let's say. The lambda vector is for the unknown coefficients that I'm looking for in the inverse problem. So there are many, many possibilities just using the basic methodology of neural networks to solve not only the PDEs, which is the direct problem, but to solve also PDE direct problem, just looking for the mapping. Inverse problem, I must add a term which includes the coefficients that I'm looking to invert. And then it's just a matter of, then I have an L, and all the neural network, it only wants me to give it an L to define the L. How I define that L, that's up to me. Okay. I have freedom of choice in the L, the form of the loss function. So now I take advantage of the fact that I have freedom of choice by adding extra things. So I have a okay, just to say that recently, about a year ago, some very good mathematicians in Zurich at Mishra and Molinaro at ETH in Zurich. It's not 2021, it was 2020 and 2021. Okay, they started to do some real error analysis. An applied mathematician likes to see some error. We want to have some error bounds. So you can do some error analysis on this approach that I showed you before by decomposing the error. But if you're interested to see a theoretical analysis of why what I showed you before theoretically also has, if you like, call it convergent analysis, you can see this in the papers 3 and 4. It's not number 34, but it's 3, 4. These are two papers which explain to some extent. There's a paper in 2020 of Mishra and Molinaro, and I think since then they've added 1 or 2 papers. So this is basically the last 2 years the stuff has been going on. It hasn't been done before. Okay. I'll give you a very quick example and to show you how it works. So this is something we know, we've seen. Take the heat equation, a parabolic equation. I could have taken a wave equation, whatever you like. Okay, so we feel, you know, mathematicians, we like to see differential equations. Here's a very nice differential equation that everybody I know, and we know that lambda is in general it's in general a matrix, a tensor anyway with left. That's not really important. So we have a classic parabolic equation, du dt minus, if lambda was constant, the material properties were constant, then it would be minus Laplacian, minus lambda Laplacian of u equals f. So this is just the classic heat equation or diffusion equation, whichever you like. It's diffusions also. It describes to some extent also diffusion of anything, heat, pollutants in water, etc., even air pollution. And Dirichlet, Neumann boundary conditions. You have a Dirichlet boundary, or we call this Robin conditions, yeah, and some initial conditions. So we know this is a well-posed PDE. Okay, and I'll show you how you're going to solve it using neural networks. Okay, so direct problem. We remember. I give you lambda, you compute u. We know now. You know we're going to say, oh, that's easy. Okay, it's not always easy, but relatively easy compared to what we want to do. Inverse problem, give you U, I'll ask you to find lambda. That's the inverse problem. Okay, lambda here is just the material parameter, but I said lambda could be here, it could be here, it could be there, it could be here. The inverse problem theory doesn't really care where you put the lambda. You can put it anywhere you want. Okay, I told you when I formulated the inverse problem, I used very, very general operators and no constraints whatsoever. So this is why it's a very powerful theory, because in fact you can use it to solve an extremely large variety of problems. So we know that. So how are we going to do? This is what we're going to do, right? So here's the basic thing. This is that came out in the original papers in 2018 or 2019. They called it PI and PIN. They call it physics-induced neural networks or physics-constrained neural networks. There are many names, but it doesn't really matter. It means how do we constrain a neural network by the physics? Okay, we start with a neural network. So we start with a neural network, and it gives me U hat, because it's not going to give me the true U. U is the solution. It's my Y, if you want Y equals f of x. Okay. Then what I'm going to do is I'm going to take that U hat, because I want to get a loss function that respects the physics. To respect the physics, I'd better, because I have a model, in this case, I can do automatic differentiation and calculate d dt, du hat dt, d2u hat dx squared. I can multiply by the identity to get the Dirichlet boundary condition on the border, on the boundary, on the Dirichlet boundary, and I can take ddn, automatic differentiation, to verify or to calculate the loss or the contribution to the loss function of the Neumann boundary condition. I put that all inside the loss function, and I say to the machine learning, minimize, and off it goes. It uses stochastic gradient, so it's extremely efficient for very large dimensional problems. And there you go. So I've just used a fully connected neural network. This is what I showed you right at the beginning. This is just a simple. So you see the NN is still there, the neural network is there, and then I take the output of the neural network, and to make sure that the solution I find respects the physics, I just put the physics into the loss function. I don't solve the physics in any way. I just put the physics into the loss function. And how do I do it? I have to differentiate. Oh, you say, but how am I going to differentiate? Autograd. Autograd built into all the machine learning and deep learning libraries all have autograd functions. Why? Because they use them to find the WI also. So I'm going to use them for another reason. And they do it in a very efficient way. I won't go into it. It's extremely efficient and extremely well done, much better than, because before machine learning came along in the weather forecasting and the oceanography community, there were what were called, there were codes, there was a lot of work done by applied mathematicians in numerical analysis on automatic differentiation. But they never reached the level of sophistication that has been reached by the machine learning people. The machine learning people really got it down. They really pinned it, they really nailed it down, we say in English. They really nailed down the problem, and they found an extremely efficient way by creating a computational graph. It's quite complex. It's computer science, right? And using computer science, they solved a mathematical problem of automatic differentiation in a far more efficient way than anybody, and there have been books written by mathematicians on automatic differentiation, by mathematicians. And the performance and the accuracy of the classical mathematical methods are nowhere near what has been achieved by the computer scientists in the last 4 or 5 years. And why did they achieve it? Because it was pushed by machine learning. And machine learning was pushed by Google and Facebook, and there was a lot of money, and they pay ridiculous salaries, so they get the best students. They finish the best mathematics students in math. They finish their PhDs, up, they go to Google, they go to Facebook, and they develop algorithms that we can use, right? And that's why the algorithms are good. It's not computer scientists who develop these algorithms, or some of them are, but there are a lot of the best brains in the world, and you go to Google, Facebook, and it's full of foreign people. It's not Americans who are doing it, don't worry. It's Europeans, Asians, Chinese, Indians, anything but US. So the whole world is going there. And as a result, if you concentrate the best brains in the world, you end up with having good software. Software built upon good algorithms, algorithms built on good mathematics. So that's why I can say you can trust. It's not just, computer scientists having fun saying this is a dog and this is a monkey, or whatever, right? Translating speech is important. That's difficult work, but they've been doing that as well. Automatic speech translation, what we call natural language processing. So you see, I use the fully connected neural network to approximate U at selected points with training data. Then I use AD, autograd, to compute the derivatives. And then I just minimize the augmented weighted loss function. There's weights. Okay, it's not as simple as I said, because the loss function has to be weighted. You don't want to give too much importance to some, to certain terms and not to others. There has to be a balance between the terms in the loss function. That goes back to basic optimization theory. There's always a problem with selecting the weights. When you have a composite loss function like we have, there's always a problem of balance between the terms, and that needs some tuning. We call that hyperparameter tuning. You don't get away, you're not going to get away for free. Huh? You're going to have to pay something. To pay is you have to do some tuning so that this loss function indeed gives you a good minimum. Okay, so you see, this is it. And I've taken the best of machine learning. I've taken my PDE, but I'm not solving the PDE. Huh? Nowhere do I solve the PDE. There's no finite element, there's no finite difference, there's no nothing. Okay, supposing that I have the data. If I don't have the data, I can also, if you don't have enough data, you can use your model to generate additional data. You can enrich your data set. Sometimes you say, oh, well, I don't have enough data, how am I going to do it? Well, if you have a good model that you trust, even if it's approximate, well, let's say it's good, you can run a few runs, a few very accurate runs, and use the results of your computer runs, your computer simulations, as additional data. So you can have more data. We call it synthetic data. Synthetic, it's not real data, synthetic, because you made it yourself, okay? But it can also be used. So anyway, then you notice that using the PIN for the inverse problems, I said no modification of the neural network. I just augment the parameter vector in the loss function to include the sought for coefficients of the inverse problem, just by including a supplementary loss. And that's all, folks. That's it, you know. So this is the direct problem. I want to solve an inverse problem. Ha, trivial. All I have to do, add a term to the loss function. That's it. Okay, that's it. I say that's it. But after hyperparameter tuning, okay. Each computation takes a long time. You'll see if you take DeepXE and you try to run it, so you'll see very soon on a laptop, it just won't. It'll take too long and you won't have enough memory. Just to say that, okay, somehow I'm going to have to, the neural network is going to use a very, very high dimensional approximation in able to capture the complexity of the PD, the unknown PD. There's a complex phenomenon behind. But as I said, you have the universal approximation theorem. So in theory, it's definitely capable of capturing the complexity. Okay, but there's a price to pay. The dimension of your optimization problem, because we convert it into an optimization problem, looking for the good coefficients of the mapping from X to Y, comparing Y hat neural network output to observations. It's going to cost us something. Okay, mathematics, the theory is good, but in practice, we have to work hard to get the benefits of the theory. But otherwise, the inverse problem, I've been bothering you for 3 days about inverse problems, and here I say, but you can solve it just like that, add a term. You say, wow, but why is this guy been wasting our time? Because it doesn't always work, and if it works, is it working well? And then it's good to know the real theory that I showed you before, so you can do diagnosis and know what's going on. Is the solution good? Why is it good? When is it good? Etc. etc. Okay. Okay, so there are many advantages. It's mesh-free. It uses what's called a strong differential form, so it avoids discretization. All that you've been taught in numerical analysis by some people, discretization, stability, numerical integration, throw them out. That's what the computer science say. And it's like, oh, what are these professors have been bothering us for years about all this stuff. And here, Mr. Mark Asch comes and says, well, you know, you complain about all that because we've got something new, right? Machine learning, but okay, but don't have it. As I said before, it's not a magic wand. It's not an abracadabra. You tap 3 times and you say abracadabra and you solve complex problems. It's not easy, but in theory it is. The theory is beautiful because for me it's great. I mean, it's everything I've dreamed of, but okay. And the other very important advantage is it has no problem whatsoever with noisy or uncertain data. Okay, it's not like a PDE, whereas if your data is uncertain, or if you have any noise, then you cannot use PDE theory anymore because things lose their differentiability. Okay, you have to work in weak formulations, and even weak formulations might not be okay, etc., etc. Okay, so that's because machine learning is made to work in noisy environments. Okay, so that was one of the the basic concepts of machine learning and deep learning was it had to deal with reality, right? We don't want to, it wasn't done by mathematicians, machine learning, and done by computer science to want to solve real problems. Okay. And we use what's called mini batch cat. There are many techniques that have been developed by the machine learning people. Okay, for them it was for image recognition or computer vision and for natural language processing. But along the way, to solve their problems, they developed a lot of really fantastic techniques that us applied mathematicians, we wouldn't, either we didn't get there. They got there because they were pushed maybe by a lot of money or maybe by a very rich environment. As I say, they managed to gather the strongest young brains in the world, all sitting together on that. And you do like that, it's like a nuclear reaction, you know, you put all these strong brains together and then it explodes. So they've done amazing things. Okay. And you can, as I said, you can achieve incredible speed ups of order 10 to the 3, 10 to the 4. Once you have a trained model. That's my sumo diagram. Remember the sumo diagram. This is not, I'm not making it, not making publicity for Google or whatever, you know. This is true. This is an applied mathematician who's very critical of these methods to say, but wait, if you take the trouble and the time and the trouble, use the neural network, at the end you get a prize. What's that prize? 1,000 to 10,000 times faster. Okay. Imagine a 10,000 hour computation being done in 1 hour. Okay. That's amazing. Then you say, wow, okay, I'm going to have to work a bit. It's going to cost me some sweat and some tears. But if I get there, the prize is fantastic. Okay. Okay. So that's the aim. Otherwise, it's not worthwhile. It's not worth our while wasting our time trying to do these things if at the end it doesn't give us any advantage over our classical methods, our classical finite difference, finite element, Runge cut, or whatever, etc., or even inverse problem. Okay. So okay, there's some disadvantages. When I say it's a terrible optimization problem, okay, it looks very nice on paper. I formulate the optimization problem, but it's terrible. Okay, though every day on arXiv, which is where things are happening, people are coming up with solutions to the fact that the optimization problem is a difficult problem and ways to get around it. So there's okay. The network or the architecture that you use in remember I had my little neural network on the left of the diagram. It's quite problem dependent, so you don't really know which one. Convergence can be sensitive to the initialization, so you might have to do some kind of what's called cross-validation or what we call random repeats. So you know it's not an easy problem to solve, and it requires hyperparameter tuning. The size, what's called learning rate, that's the step size in the gradient computation, the number of residual points. I call this the no free lunch. It's known as the no free lunch theorem. You don't get lunch for free. You're gonna have to work to get your lunch. Okay, but it's recommended for, okay, there are different recommendations. I won't go into that. We don't have time. Okay, then I just showed you one way, but very briefly I'll show you. There's another approach which may be interesting. Well, it has pros and cons. Okay. Which is called, instead of learning, there I was learning the solution. Huh? Yeah, you can learn the operator, you can learn G, and you use the theorem of Chen and Chen to create a neural network. You see naturally here in the theoretical formulation, we have what's called a branch and a trunk. So we can translate that into a composition of two neural networks, one that does this part, this summation, and one that does the nonlinear part, okay? And if we can create two neural networks, and this is what is done with the special architecture, then one can learn the operator G. Yeah, we're looking for the operator G, not the solution, not you. We're looking for the operator, which is the mapping, not just, okay. So anyway, I'll give you references here. There are two, the main, if you want to Google it, it's DeepONet. This is the same student, PhD student who developed DeepXDE. He went on to develop DeepONet. There's a couple of students, there were two students, PhD students. They left, they became professors themselves, and they've developed since then, starting from the original DeepXDE, which was learning the solutions, a method that learns the operator. So it has certain advantages. It looks basically like this. So basically you give U and you give Y, and you end up with an approximation of G of U of Y. Okay, so this is, it's another concept, but it's based on the theory of Chen and Chen. I won't go into it, but then you can predict the function, and you use training. I won't go into it, but it also, it can be shown, can be relatively fast compared to the previous one that I showed you. Can overcome what's called the curse of dimensionality, and it's very, apparently it works very well for multi-scale and multi-physics problems. You learn the operator and you don't learn the solution, okay? But it has no guarantee that physics is respected. It might require large training sets. So the latest idea now is to combine the two, to take the physics constraint and the depot net, and to add another term to get the best of both worlds. And in this case, we have respected the physics, and it's very good for what's called parametric studies. I give the references. You see the references are all, they 21, 21, 10, okay, 21, these came out in October 21, and they're even more recent papers. When I gave this talk in December 2021 originally, I was using references from 2 months previously. So references are coming out. People are doing work, a lot of Chinese, only foreigners, but they're all in the States. They're not working for Google yet, but they will one day, or for NVIDIA or whatever. But they're all foreign people. Okay, and so there's this new method. So okay, so basically it looks like this. This is the diagram of the depot net with physics constraints. Physics constraint. Okay, AD, I don't have time to go into AD, but AD, you can come back to my slides. I just want to show you a quick example that I've been working on personally. But AD, we've been using, there's an explanation of AD in my slides, and I told you that it's equivalent to the adjoint method. And as I said, today it's built into all the important machine learning frameworks such as TensorFlow and PyTorch and other things use automatic differentiation. And so basically it solves the same problem. And this is because we've done this the last 3 days. This talk I gave to people that I didn't give a course to before, so I had to include, this is all stuff that we've seen already. Okay, so we've seen this over the last 3 days. I'll just show you an application that I'm interested in, that I've been solving with my students. So we're interested in biodiversity of whales, and one of the whale species that's endangered is the sperm whale. So we have a team of divers, fortunately, and they have, these are microphones, these are stereoscopic microphones we call hydrophones. It's just a microphone that goes under the sea. So this is very, what's called non-invasive surveillance. We're not bothering the whales at all. We're just listening to their calls. And why can we listen to their calls? First of all, the sperm whale has this extremely sophisticated language. They use a lot of communication, different types of communications. They can communicate over very long distances, and they use the sonar, which is their communication, to hunt also. They use it as a sonar, right? So it's also the sperm whale, it's because it has all the sperm. It has all the sperm in its head. That's why it was hunted almost to extinction, because it has a lot of fat, a lot of useful fat inside. And this sperm whale is endangered, and we'd like to understand its social behavior. And by measuring, all of this by measuring sonar signals, because you can't really capture these things. They're too big. It's not like a dolphin or something. You can capture it and let it go and investigate. These guys are, they're big, really big. I haven't been under the sea, but I've seen movies. I maybe give a reference. There's a couple, there's a video on YouTube that you can look at, which tells the story of our research project. I think I'll give the reference somewhere. If not, I can send it to you. So we're measuring these clicks and their communication, possibly also to understand their social interactions, to count how many individuals, and we can also determine the age of the individual by measuring the click, because there's a difference. There's a primary and a secondary click, and that has to do with the physiology and the anatomy of the whale that's emitting it, and from the distance between the two, we can have an estimation of the size. So we can also follow their growth by using sonar. It's amazing. And why sonar? Because in the ocean, sound travels incredibly efficiently. You know, the blue whales can communicate intercontinental. They can communicate from the Atlantic to the Indian Ocean. They have a communication. A blue whale in the Atlantic Ocean or in the Pacific can communicate with a blue whale in the Indian Ocean. Okay, the sonar is incredibly efficient, especially in water. So anyway, and we can use it for biodiversity monitoring and monitoring for endangered species. We do this for dolphins and for many other species, killer whales in Vancouver, off the west coast of California, of Canada. We have students in the group that I work with that are also looking at killer whales and using acoustic passive, we call this passive acoustic monitoring. We're not emitting any signals, any sounds, because if you make noise, and that's one of the reasons also we have to protect them, the noise bothers, it interferes, it perturbs their communication, huh? And it disorients them. Don't forget they use their sonar for navigation also, to detect objects, to detect prey. They have to eat a lot. Anyway, so that's the motivation. And then we've been working on, so we have a three-dimensional mesh model of the anatomy of a sperm whale. The problem is that we don't know the material parameters. We don't know what's going on inside the head because you can't catch a sperm whale, right? It's a bit too big. And even if you caught it, you couldn't put it into a scanner, or you couldn't take pieces off to see what's inside. So we really don't know what's going on inside its head. This comes from post-mortem. Sometimes the sperm whales, you know, they die and they wash ashore, and then you can bisect them. But a dead sperm whale, the tissues don't have the same properties. It's the tissues that are important. The red is bone, and all the other colors are different tissues. They're fat. We've got lenses of fat and blubber and other things, and the sound actually comes out in front here. Okay. And around this, we surround it with water. We just deal with the head because the rest of the body is not important for the sonar. It's just the head. That's its mouth, if you know, in the front, and this is the back of its jawbone. So we'd like to solve an inverse problem to characterize the tissue, and if we can characterize the tissue, then we can understand and reproduce. We can have what's called a digital twin of the sperm whale, of how its sonar system, how it communicates, and how the sounds come out and how they're generated. So that's the problem. So, okay, mathematically, to start off, we can start often with we might have a student and say, well, this problem, okay, we would like to solve this one. The direct problem for this is no problem. We have one of my students who's now a postdoc, he programmed a direct problem, but the inverse problem is much more complicated, obviously. So to start the inverse problem, you don't try and solve the inverse problem there, you solve the inverse problem on something that's approximate. And once you tune, I told you there's a lot of tuning parameters to do. You do all the tuning on a simplified model, and once that works, you go back to the real model. That's the way we do research, right? We don't try and solve the most complicated problem first. We try and get experience on simpler problems, simpler formulations. The problem is still complicated, okay? And okay, I won't go into it, but there's the wave equation that you saw the other day with Maria, and okay. There's I give references here. My student's thesis is online, and we're busy doing the inversion. The inversion is a long story. So his thesis came out in 2020, and you can get it. I give the reference somewhere here, and okay, that's it. Thank you.